Hi. So now we're going to start a new chapter, chapter 14 on polymer structures, and we're going to be discussing what the general structure and the chemical characteristics of polymers are, what are the common polymeric materials, how they differ chemically, and in the crystalline state in polymers, is it different from metals or ceramics? So the word polymer comes from it's a compound word. Poly means many and mer means a repeat unit. So you might be very familiar with a lot of the polymers out there on the market or the plastics out there on the market. You got your polyethylene and the repeat unit is these two carbons attached to these four hydrogens, and it just goes on and on and on. Polyvinyl chloride or PVC, two carbons, three hydrogens and a chlorine, going on and on and on. And polypropylene, two carbons in the chain, three hydrogens attached to a group on the side that has a carbon and three hydrogens on it. And that goes on and on and on. So you can see that what you've got are these what are called monomers, and then they repeat over and over again into a very long chain, and that's a polymer. Now, we've been using polymers for thousands of years. Originally, we used natural polymers like wood, cotton, leather, rubber, wool, and silk for many different uses, of course, for clothing and for weapons, for things like that. The oldest known uses of polymers include rubber balls that were used by the Incas to play games, and pitch, which is a natural polymer which was used on boats on the bottom to keep the boats watertight. So most polymers, of course, are long chains of hydrocarbons. Hydrocarbon, the word, means a combination of hydrogen, hydro, and carbon. Saturated hydrocarbons means that it only has single bonds. So, for example, ethane, C2H6, has two carbons. A carbon, given its position on the periodic table, you know it wants to have that filled outer valence shell. So carbon can bond to can form four bonds. So here in ethane, if you look at the carbon on the left, you've got three hydrogens, and then it's also bonded to the carbon for a total of four bonds. And then that fills up that outer valence shell. It's full and happy, and all the bonds are filled. Now, you might have heard of a lot of these compounds right here: methane, ethane, propane, butane, pentane, hexane, it goes on and on. These are the paraffin compounds. The prefix here, the meth, eth, pro, but, those things tell you how many carbons are present in the compound. So methane means one carbon, ethane 2, propane 3, butane 4, pentane 5, hexane 6, heptane 7, so on and so forth. Octane, probably heard of that one, and gasoline, that has 8. Now, as your carbon length of your molecule gets larger, you can see that it has an effect on the boiling point. As you add more carbons, your boiling point goes up. So to talk about some of the compounds in terms of what they're used for, I made this funny little graphic. Methane is fart gas, so you're probably super familiar with that one and have been since birth. Ethane is used in the production of ethylene for making plastics, antifreeze, and detergent. Propane and octane, you're probably really familiar with those compounds for burning of the fuel for your car or to cook food. Hexane is a solvent that's used to keep rubber cement liquid, and it's also used in a lot of thermometers. And butane is a lighter fluid present in a lot of lighters. So there's some of the uses of those things. Now, you have unsaturated hydrocarbons, and that means that they form double and triple bonds with other neighboring hydrocarbons. Saturated hydrocarbon basically means that all of the carbon's bonds are filled with available hydrogens. Okay, so it's saturated with hydrogen. It's full of hydrogen. And so that would mean that, for example, in methane, it's bonded to 4 hydrogen atoms. In ethane, the carbon only forms a single bond with the neighboring carbon atom, and it's bonded to 3 hydrogens. But if it forms double and triple bonds, then it's not saturated with hydrogen, and so it's called an unsaturated hydrocarbon. Unsaturated hydrocarbons are more unstable. They can oxidize more easily. They're more reactive. They burn. For example, ethene, ethylene, or acetylene, ethine, these things burn a lot easier. They're more reactive. You might have also heard of saturated versus unsaturated fats. So the fats are made of fatty acids, which are these long hydrocarbon chains that have a carboxyl group or a COOH group on one end. So to make a normal fat, you take the fatty acids and you bond them with glycerol to make a triglyceride, which is shown here on the right. Saturated fats, like the ones made of palmitic acid, those are bad for you. And so they're solids at room temperature. But the unsaturated fats are better because they're liquids at room temperature, and so they don't clog your arteries. So that's one reason. There's other reasons listed here on the slide. If you want to learn more about it, of course, I saved these slides underneath the lecture, and you can read on. Isomers. Isomerism is when two compounds with the same chemical formula have different structures. For example, you can have C8H18, and that makes normal octane with 8 carbons hooked to hydrogens all around, okay? But that same chemical formula, C8H18, could also be structured this way right here, 2,4-dimethylhexane. So in that, the long chain only has 6 carbons, 1, 2, 3, 4, 5, I'm sorry, 6. And then that one goes on to have these side chains, okay? So the side chains make up the rest of the molecule. The chemical formula is the same, but the structure is different, and so the properties can also be different. Specifically, isomers can differ in the way that the atoms are connected. That's called constitutional isomers. For example, here you have butane and isobutane. But isomers can also differ in the way the atoms are arranged in space, and those are called stereoisomers. Specifically, you have cis versus trans isomers. Cis, the side chains are on the same side of the molecule, and trans, they're across from one another. Oftentimes, isomers have similar chemical properties, but different physical properties, like the boiling point. There's a lot of common hydrocarbon groups. If you've ever taken organic chemistry, you're really familiar with some of these. Alcohols is when you have a unit. Here the unit is symbolized with an R, so it's supposed to be generic, like a variable. And then this unit is hooked to an OH group. So you have methyl alcohol, probably everybody's favorite ethyl alcohol, and so on and so forth. Ethers are when you have two different groups hooked together by an oxygen. And so this is dimethyl ether. Methyl because it's the CH3 group, meth, remember, for one hydrogen, right? So you have two of them, dimethyl ether, hooked together by an oxygen in the middle. Acids, organic acids, are when you have some kind of group that's hooked to this group right here, a carbon double bonded to an oxygen, and on the other side, the other available bond for that carbon is hooked to an oxygen, which is hooked to a hydrogen, okay? So that's an acid. So that's how you form your organic acids, is if you hook this COOH group onto the side there. For example, this one right here is acetic acid, which is vinegar. 2 carbons, right, and this carbon with the 2 oxygens and the hydrogen is your acid group. Aldehydes, like formaldehyde, you have a group here, this generic group, that's hooked to a carbon double bonded to an oxygen, which is also bonded to a hydrogen on the other side. So formaldehyde is the simplest one, and it's just the R group is just a hydrogen over here. Of course, we use that to preserve bodies in the olden days. And then you have your aromatic hydrocarbons. Your aromatic hydrocarbons have this ring here. Now this structure denotes what's called a phenyl group. In a phenyl group, you have 6 carbons arranged in a ring like that. And then you have these conjugated double bonds. So you have a carbon double bond here, single bond, double bond, single bond, double bond. As you'll read if you or watch in the lectures, if you go further with it, what happens is actually each carbon here is bonded 1.5 times. Really, these extra bonds are sort of shared in this ring structure. So it makes a very nice stable structure because those extra electrons are shared by the whole ring. Okay, so an aromatic hydrocarbon is when you have this phenyl group hooked on to some generic thing. So for example, this is phenol right here. Okay, So that brings me to the end of what I wanted to say about this. If you want to go into more depth, learn more information about all these things, I highly recommend watching some of those crash course chemistry videos that I have placed in this section. You've got your intro to organic chemistry, a description of alkenes and alkynes, a description of aromatic groups, and it goes further into a description of all those things. And the speaker, the presenter, is really engaging and funny. He throws in a lot of great history, and I think it'll help you understand all of these things a lot more deeply. Okay, so thank you, and I'll see you later.